Now, you are live now.
Okay, so very good afternoon, friends. So continuing the topic of design of bolted oblique screwed joints from the previous lecture, today we'll discuss the eccentrically loaded bolted joints. Now, when we say eccentric, so yesterday we have gone through the eccentricity and we have understood well about the eccentricity of a loaded element. Now, in this slide, I'm repeating this two slides. So the first case which we are dealing with is eccentric load acting in the plane of bolt. Now, when we say in the plane of bolt, it means that the bolts are lying in this plane. So if this is the plane in which the number of bolts are lying, then the load is acting in the same plane. Now, it is acting in the same plane. That's why it is known as or called as in the plane of bolts. So again, all these four bolts, 1, 2, 3, and 4 bolts will be subjected to primary shear force by virtue of their position, which will try to hold this particular plate. The secondary aspect is secondary shear force because of the moment that can be determined as follows. Now, when we say as follows, you have to consider this diagram which I have depicted here to show the primary and a secondary, basically secondary shear force, because the elements that is rivets which are there or the bolts which are there, please try to understand this fact. I think this is visible. So the visibility is there. So the entire setup will try to overturn this plate, because the eccentric load P, which is acting here, eccentric load P, which is acting here at a distance of E from this particular, so at this place, so I think it is quite visible. So P into E, that E eccentricity is the distance of CG or centroid of the bolted system. So this will try to overturn this bracket. Now in that case, it is the bond duty, of each and every bolt to resist that overturning. Now when we say to resist that overturning, it means that these bolts or these rivets, one and the same thing if it is eccentric, so this will try to resist this particular turning effect or turning moment. That's why it is equated. So R1, R2, R3 and R4 are the respective distances of these bolt centers from the CG of the system. And P1 double dash, P2 double dash, P3 and P4 double dash are the secondary shear forces, which are nothing but proportional to their distances from the CG, the distance of rivet from the CG, and thus it has been written as P1 double dash is directly proportional to R1. We will introduce a constant of proportionality and we will try to calculate this constant of proportionality in terms of P into E upon the square of distances from the CG of the system for rivet number 1 to 4. I hope you are getting this point. So similarly, we will calculate, say for P1 double dash, we will calculate this with respect to R1. Again, the same thing if we want to calculate P2 double dash, P into E into R2 upon R1 square plus R2 square plus R3 square plus R4 square. It means that for P1 double dash, P2 double dash, P3 double dash and P4 double dash, we'll have to change only R1, R2, R3 and R4. Now, since we have calculated P1 double dash to P4 double dash, now the resultant. The primary shear force and the secondary shear force may be added vectorially to determine the resultant shear load. That's why R, the resultant shear load on the rivet, is P single dash, plus P double dash plus twice P dash P double dash cos theta, where what is theta? So angle, included angle between primary shear load and the secondary shear load, which can be very well calculated from the above diagram itself. So say for P1, say this is say P1 double dash, and say P1 dash, and say this is P1 double dash. So in that case, this angle would be theta 1. So theta 1 would be calculated directly with reference to the diagram, and then we'll have to calculate, say this is the calculation for R1, then R2, then R3, then R4. All the 4 values can or may be calculated. Otherwise, the farthest bolts may be or must be calculated. So now after getting R1, R2, R3, R4, you have to calculate R1, R2, R3, R4, and you have to find the most heavily loaded bolt out of this, and then about this most heavily loaded bolt, maximum value will be selected, and based upon that maximum value, we have to calculate the diameter of this particular bolt. Now, as far as the diameter is concerned, this diameter would be DC, root diameter or core diameter, and that can be well converted by using 0.8 into nominal diameter, so that we can very well calculate the nominal diameter of the bolt. Okay. Next is eccentric load acting perpendicular to the plane of bolt. Now, here in this case, the plane of bolt, just like say, to understand this particular condition, we have cloth hangers in our home, wherein we fix those cloth hangers in the wall and we put our clothes perpendicular. So the axis of the bolts are perpendicular to the wall, Now, let us consider this example wherein these bolts, 2 bolts in a row, that is row 1, the upper row and the lower row. So in each row we are having 2 bolts. Now this P will try to topple the bracket. Now when I say topple the bracket, it means it will try to stress the bolts. Now, what would be the different types of stresses that will act, or different types of forces that will be acting at this juncture? So, number 1, due to this eccentric load or simple P, this P, all the 4 bolts will be subjected to direct shear. So, direct shear will be there on these 4 bolts. So, direct shear. And the secondary one is, now with reference to this bracket, if I am applying some eccentric load, this bracket will, with reference to this edge C, it will try to overturn the bracket. Now in this case, whatever may be the bolts are there, it will get stretched. Or when we say it will get stretched, the type of stress would be known as a tensile stress. Now in the previous example, it was all about shear, primary shear and secondary shear. But now in this case, we are having primary shear but secondary tensile. So there would be 2 nature of stresses in this type of arrangement. So the very basic element, that is the primary shear element, is P1 dash is equals to P2 dash. We'll get the same thing, divided by number of P divided by number of bolts. Now due to eccentricity, again the same thing as we have seen in the previous example. Again it will try to topple, it will try to overturn the bracket. So again, there would be constant of proportionality. So C into L1, and that too depends on the distance. I'm again repeating this particular part. Say this is L1, this distance is L1, and this distance is L2. So L1 will be more vulnerable, or L1 will be more prone to this particular overturning, because as we go on increasing the distances, the chances of tensile failure will be more, because here the edge is supporting this. So the next element is we have to calculate secondary tensile strength. Yes, secondary tensile strength. So again, the same thing with the same distances, but now here it is L1 and L2. Previously it was R1, R2, R3, and R4. Now here the distances are with reference to the edge C. It is L1 and L2. Why this figure 2 is there? Because two bolts are there in a row. Because this L1 is the distance of two bolts which are in single row from the base C, or the reference is C. So we'll get P1 double dash and P2 double dash. Bolts farthest from. Now again I'm repeating. Which one will have maximum value of stress? So obviously the bolts which are farthest in tension, obviously in tension. So we may say that the bolts at 1 will have maximum stress, which can be determined by simply calculating the equivalent tensile load and equivalent shear load. Please mind well, we have to calculate equivalent tensile as well as equivalent shear. But generally, equivalent tensile load is always having more magnitude as compared to shear load. That's why for the simplification part, we are only dealing with the equivalent tensile load. PTE is equals to half P1 double dash plus P1 double dash plus 4P1 dash. This P1 dash is nothing but the shear load. This is the shear load. Now, after getting PTE, bolt dimensions can be very well get by PTE is equals to pi by 4 DC square into sigma T. Again, I am repeating, this DC is the root or core diameter. You have to calculate nominal diameter, and that nominal diameter will be get by substituting in the equation or from the data book. DC is equals to 0.8 times of D, that is nominal diameter. Now we have come to the last part of this particular screwed or bolted design in eccentric planes, and that is eccentric load acting parallel to the plane of the bolts. Now just take the example wherein some bracket is fixed, like this bracket is fixed on the ceiling, and bolts are there in this fashion. So the ceiling plate and the bolts are there in this fashion, and the load is again applied in a downward direction itself. So parallel to this axis, parallel to the axis of the bolts. That's why this is parallel to the plane of the bolts. Now in this case, again, one has to have a tilting edge. So here in this diagram, you please concentrate on this tilting edge C, because since the load is eccentric, the center of gravity of the bolt will lie somewhere here, bolting system, but the eccentricity will be considered from the tilting edge only. You please keep this thing in mind. That's why the eccentricity of the distance will be considered from the tilting edge now, because the entire P into E eccentric loading would be taken with reference to this C, that is total distance is E. Now the process will be the same, but in this case, how the bolts will be stressed? See, since the plate or the brackets are on the ceiling, for the sake of understanding, so all the bolts will be under tension, because the load of the self load of the bracket will try to pull it down, so the bolts will be subjected to tensile load or the tensile effect. Secondary, when this P into E will come into force or play, in that case again it will overturn with reference to C. So there we say that again primary was also a tensile, and now the secondary will also be a tensile. So now the very basic element is we have started with both the shear. Now one shear and one tensile. and now third, both the tensile. And again we have to add this two effects. Now again the same repetition. Primary tensile forces are given by P1 dash, P2 dash, P upon number of bolts. Secondary, the same thing, nothing new. Total tensile, you have to add these two forces. The effects are to be added, and then as the bolt at 1, I'm repeating this step. Why? Yes, see the bolts at 1. This is 1 and this is 2. So the bolt nearest to the tilting edge will experience minimum tensile effect as compared to the bolt which is farthest from the tilting edge. And that's why we may say that the bolt at the 1 will experience maximum resistance, and that's why calculating sigma T1, if you want to calculate DC, the formula would be, sir, P1 is equals to pi by 4 DC square into sigma T1 or sigma T, doesn't matter, but P1 matters. So P1, it is the highly stressed or highly say stressed bolt at the distance L1. So this is how we can calculate the load on the bolts subjected to eccentric load acting parallel to the plane of bolts. I hope you have understood these aspects of bolt design. Now we'll try to cover up some numericals which were asked in the previous years. So starting with 1 mark question, as you can very well see, bolts in the flanged end of a pressure vessel, obviously pressure vessel, are usually pre-tensioned. Indicate which of the following statement is not true. As far as pre-tensioning of the screws are concerned or the bolts are concerned, this pre-tensioning helps us in preparing as well as improving the efficiency of the joint. So pre-tensioning helps to seal the pressure vessel. Exactly, this is true, and we have to find out which is not true. Pre-tensioning increases fatigue life of the bolt. Exactly. C, pre-tensioning reduces the maximum tensile stress in the bolt. So this is dubious, this is doubtful. D, pre-tensioning helps to reduce effect of pressure pulsation in the pressure vessel. Yes, this is again very true. So the right answer is, which is not true, is pre-tensioning reduces maximum tensile stress in the bolt. No, pre-tensioning basically improves maximum tensile stress in the bolts. So the answer is C. Question number 2. The bolts in a rigid flange coupling connecting two shafts transmitting power are subjected to. Now, this is the simplest example wherein we can say that if the bolts, say these are the two coupling, these are the two flanges, these are the two flanges of the coupling, and if the, say this is the driver side, so driver side, if the driver side is trying to rotate, if the driver side is trying to rotate this bolt, then in that case the bolt will be rotated. Now when we say try to rotate, it means it will be subjected to torsion itself. It will be subjected to torsion itself. So the answer would be torsion. The answer would be torsion. So this is the second numerical question for 1 marks, where we can say that the simple knowledge of motion will be effective. Now these are the 2 marks question asked again in the previous examination. A bracket is supported by means of 4 bolts of same size, 4 bolts of same size as shown in figure 6. Determine the diameter of the rivet if the maximum shear stress is 140. Now, since all the bolts are placed in line, so CG will lie at the center. CG will lie at the center. Now, the basic element is the CG, center of gravity, finding center of gravity of the riveted system or the bolted system. So in that case, this load of 20 kilonewton will be shared by all these 4 bolts. So direct shear stress, no doubt about this, 5 kilonewton, 20 divided by 4, 5 kilonewton. This numerical is from case 1 because the eccentric load is applied in the plane of bolts. In the plane of bolts. So the load is applied in the plane of bolts. So this is the primary or direct shear force. The next one is secondary. Now, since we know the basic formulae, wherein we can say that the CG will lie at the center. And how many bolts are there? How many bolts are there? There are 4 bolts. So CG will lie. So this is 30, 30, and 30. So I'll call this bolt number 1, say bolt number 2, 3, and 4. So we can say that the CG will lie exactly between 2 and 3. So between 2 and 3 it is 15 mm. So the distance would be 15 mm. Now 1 and 4 would be at a distance of 45 because 30 plus 15, 30 plus 15. And 2 and 3 would be at a distance of 15. So this is L1. For the sake of understanding, this is L1 and this is L2 because equispaced bolts are kept. So L1 and L2 ka. So this is the square into now when we say F2, so this is the secondary shear for the farthest. The farthest distance is 45 mm. So we have calculated this. So it came out to be 16 kilonewton. Then since we know F1, since we know F2, directly we can get the under root because in both the cases we are having shear. So we can directly add it. So the answer which I got is 16.763. I think it should have been kilonewton. It should have been kilonewton. So kilonewton. It should be in kilonewton. So kilonewton again. Now please substitute this value in this equation. Since we know that the allowable shear stress is there, so we can get the diameter. The next element, next problem is given for the practice. Same problem with some different dimensions and numbers. That's it. Otherwise everything is same. So you can get this particular because you have to calculate the stress developed, maximum shear stress developed, and the bolt size is again given. So you can very well calculate it. Same type of problem. That's why I have solved one and given this for practice. So again, the same thing, practice problem is there, and I have given the answer also. In this case, again, but the scenario is changed now. All these 3 bolts are in line horizontally. And what we have to calculate? We have to calculate the resultant shear force on bolt C. Answer I have calculated, it is 30 kilonewton. So please solve these questions from the bolted joints. Thank you so much. As far as design of bolts are concerned, now we'll go for the next type of joint, that is design of riveted joint. So I'll share. So I'm sharing the screen again. So today the design would be covered for design of riveted joints and design of welded joints. I hope. I think it is fitted. Okay, done. So it is fitting to the window. No issue. Now, as far as riveted joints, see, this is the basic type of joint, whereas we generally used to call this joint as semi-permanent joint. So a rivet is a short cylindrical rod. This is the small sketch of or outline of that particular rivet, which we are much familiar in our domestic as well as in commercial purposes. And this rivet is there in the steel bucket or in the on the handle of frying pan, on the ceiling fan. So these are the riveted joints. Now riveting, the operation of riveting is to make a joint in the plate, in the structures, in the elements, and for that we have to make smooth holes first, and then we insert this element known as rivet. It is again subdivided into three basic portions. This is the head, generally hemispherical. The next one is shank, that is the body having some diameter, and the last one is a tail. Now this tail is made in this fashion just because we have to hammer it from the head so that this tail gets flattened from the other side and the joint is made. So this is how the riveted joints are made. How many different types? There are two types: lap joint and butt joint. It is quite clear from the name itself. When we say lap, it is one lap over another, and we are putting some rivet in this. So this is lap joint. The next type of joint is butt joint. Now when we say butt joint, this is nothing but the butt joint. These are the two plates which we want to rivet. Now if you want to rivet these two plates, in this case, you have to have some strap plate or some cover plate overlapping on both the plates so that a permanent or a fixed joint can be made. The very start of the types of riveted joint, lap joint. So these are the lap joint which I have explained right now. So rivet, and these are the two plates. This is nothing but double riveted. Previously it was single riveted. Only a single row of rivet is used or was used to join the plates. Now this is a double riveted plate. Two rows are used to join the plates. Now the another fashion is, say this is a parallel row, another fashion is zigzag row. So this is zigzag types of rivet or riveted joint, but this is lap joint. The second type is butt joint. See, this is the parent metal or parent plates. These are two the parent plates, and this gray model is for the cover plate. Now we have to cover these two plates with the help of this third plate known as cover plate, and then rivet it. So such type of joints are used in boilers basically. Butt joints generally used in boilers. Lap joints are also there and butt joints are also there. Like lap joint, the arrangement of rivet may be various kinds, namely single row, double row, or triple chain, or zigzag. A few types are shown in this. So this is single with single strap. So this first diagram shows the single strap plate. Here it is double strap plate to again strengthen the joint. So this is single and double strap plate chain arrangement. This is called chain riveting. This is zigzag riveting. The moment you increase the number of rows, it is generally referred to as a chain type of riveting. Now the next element. Now when we say design of riveted joint, we have to have certain terminologies very much clear with us. And these terminologies are nothing but the geometry of distances or the riveting. The number one is pitch. Generally we refer this to as the distance between two consecutive rivets, but this is a linear distance. This is linear distance between two centers of consecutive rivets in a single row, not compared with another row. And now if we are comparing with the another row, then you have to have the different type name. Next is back pitch. Now back pitch is the shortest distance between two successive rows. Two successive rows. That's why PB. So PB is the distance. The third one is a diagonal pitch. Third one is diagonal pitch. The diagonal distance between two rivets. And the fourth definition, which is very, very important and always being used for the safe design of the riveted joint, is the margin. Now, when we say margin, margin is the distance between the end of the row, center of the end of the riveted row, and the nearest edge. Yes, sir. It is the nearest edge from which the center distance may be known as margin. Now, as far as strength of riveted joints is concerned, the single riveted joint is first to be evaluated, so that we can get the idea of how to evaluate the failure of riveted joints in different modes: single riveted, double riveted, chain, double riveted, zigzag, triple riveted, because losing joints are also there. These are very strong joints. Diamond joints are also there. So number of joints are there. But first we'll have to evaluate how this joint will fail. Now when we say how this joint will fail, in this case, now the tearing of this plate, when we say the plates are there, since when we want to rivet, we have to drill the holes in the plate, in the parent plates. Now when we want to join two plates, it means holes will be drilled, and when holes will be drilled, obviously stress concentration will act. Now that's why the concept of margin M is there. But still we fill in the that particular gap with the help of our rivet, which is a strong metal. Generally low carbon steels are used in the fabrication or manufacturing of rivets. So when it is fitted and pulled, say in that case, this particular, you please concentrate on this diagram. So in this case, this may fail along or between two rivets. The successive span may get fail. That is why this is called tearing of the plate. The very first. It may fail. So the distance allowable, this is the stress, the distance P minus D. What is P? P is nothing but the pitch, linear pitch, what we generally used to call pitch or linear pitch. P minus D. D means diameter of riveted hole. So D means half D by 2 here, half D by 2. From center to center distance is pitch minus these two. So this is the most susceptible area wherein this tear may occur. And T is the thickness of the plate. The next, now shearing of the rivet. It may happen that the rivet may shear. For lap joint, we may use single strap butt joint. For a double strap butt joint, it's a double shear. So this is very simple as far as the shearings are concerned. The third type of failure which we generally consider is crushing. Now this crushing is nothing but the localized compression that occurs at this joint arena, both on the rivet as well as on the plate. So if the bearing stress on the rivet is too large, the contact surface between the rivet and the plate may get damaged. Now please concentrate on this. Yes, and this is more dangerous basically, because crushing stress is not generally an alarming stage wherein it shows, because in shear it may fail, in tension it may show that it is over elongated, but when it comes to crushing, it doesn't alarm anything. So gradually it progresses, and one day you will get the joint broken. So this is how the crushing takes place. Right? The next one. Now, tearing of the plate at the edge. This may happen. This may happen. That's why the concept, again, I'm using again and again, using minimum margin of 1.5D should be there from the edge of the plate to the diameter, or the diameter line of the rivet. Diameter line of the rivet. Diameter line of the rivet. So this may happen. No issue. So this is how so efficiency. The last thing which we want to discuss is efficiency of the joint. Efficiency of single riveted joint can be obtained as the ratio between the maximum of either P1, P2, P3. Now what are these P1, P2, P3? These are nothing but the, yes, this is P3 in crushing, this is P2 in shearing, and this is P1. This is P1. So out of these three, if you want to calculate the efficiency of the joint, then minimum of this divided by the dimension, you'll get P into T into the allowable stress, allowable shear stress, you'll get efficiency of the joint. Now, as far as numericals, as far as the different types of riveted joints, I just wanted to add one thing here. Eccentrically loaded riveted joint. Yes, eccentrically loaded riveted joints are there. And these joints are nothing but the eccentrically loaded bolted joints. That's why I have not covered that particular part in this presentation, because that we have already covered in the last lecture, or in the last say topic, wherein we have, in design of bolted joint, we have covered that in the plane of bolt. So these are nothing but the basic elements of design of riveted joints, along with the eccentrically loaded riveted joint in the plane of bolt. The load is applied in the plane of bolt, and that load we have already covered. Now moving to the last topic, that is design of welded joint. When we say, because the numerical will be covered for the design of riveted as well as for the design of welded, it will be covered in the next lecture. So design of riveted joints. As far as welded joints are concerned, this is much familiar joint for all of us, wherein this joint is made by fusing joining of similar or dissimilar material by fusing some filler material. Sometimes we may require some filler, sometimes we may not require some fillers. So this is the basic description. Now we are much interested in types of welding and then how the welded joints fail, because we have to design it. Now, as far as types of welding is concerned, the welding processes can be broadly classified into two groups. Number one, that is very important, is fusion welding. You please listen to these words, because it looks like that this is a theory part, but for 1 mark question, this is very important, because the questions will be solving in the very next lecture. So you will find these things there only. So please mind well, for 1 marks question, this theory is very important. Now, fusion welding process. Fusion welding process use heat to melt the base metal. Now, this is the very common type of welding process, wherein heat is used to melt. In fusion welding operations, a filler material or metal is used, generally added to molten pool. So fusion welding process can further be subdivided into following types. Please carry on with this. So fusion welding may be subclassified as, say, I must add, say, A, arc welding. arc welding. So this is arc welding. Now, what is arc welding? Arc welding refers to a group of welding process in which heating of metal is accomplished by an electric arc. That's why we used to call it as a general arc welding. Now, the next element, which is again very important, resistance welding. So resistance welding achieves. How does we achieve that resistance welding process? How does is achieved? By electrical resistance to the flow of current passing between the fine surfaces. This is very important. Held together and using the pressure. The best example is spot welding. The best example is spot welding, wherein we pass a current, and then some pressure is applied. Some pressure is applied over that particular surface so that the welding can be properly done. So out of this, again, there are a few examples. We'll come over this issue later on. Okay. Next is solid state welding. This is again a very important part as far as solid state welding, because we use friction welding there. Solid state welding refers to joining process in which coulsons results from the application of pressure alone or a combination of heat and pressure. So sometimes pressure will act, and sometimes we may require both the things. Generally, no filler material is used in the process. Diffusion welding. The best example is diffusion welding, and we are much acquainted with friction type of welding in mechanical engineering. Diffusion welding, two surfaces are held together under pressure at an elevated temperature in the parts coulsons by solid state fusion. By virtue of pressure, at high temperature, the parts are fused together. The metals are fused together, and the joint is made. Next is friction welding. When we say friction welding, this is quite familiar term because it is achieved by heat of friction between two surfaces. So most of the industrial products are being done, solid state welding are done with the friction welding because the efficiency of the weld is very high. And the next one, which is a bit costly element, but still, ultrasonic welding. A moderate pressure is required basically, and the ultrasonic frequencies, because oscillators are being used and the contracting surfaces are oscillated and in the direction, and the joint is being made. Ultrasonic welding are very much precise elements used for the assembly purpose in industry. Again, we'll have to go back to the fusion welding, but still. So question and answer, it will be done because the type of welding is also there. So again, I'm concentrating on arc welding. So as far as arc welding is concerned, the temperature of the arc is very important. Both the metal and the non-metal, the temperature of the arc is very important. And as far as we refer generally the different types, so in that case, the different types of joints we generally made. So here, both the lap joint as well as the butt joint. The welded part is again the same. The terminologies would be almost similar as we have studied in bolted as well as in riveted. But the lap and the butt joints, lap joint and the butt joints are very much familiar and the similar elements. Before we conclude, for the types, we must first go with the previous lecture for that particular So I'm again sharing the screen. So this is the application window. Please concentrate on, because that part would be repeatedly asked in the yes, because there are a number of numericals on this issue. So please again concentrate for only 2 minutes, and we'll wind up with the today's lecture, because this is the important portion which I was expecting to be covered in Riveted also. So, but no problem. We have today only we have finished up with this eccentric load acting in the plane of pole. So these would be the formulas for the rivets also. Now, what would be the change as far as calculations are concerned? So, only change is here we'll use D. We'll use D, because D over here there is no D or DC. In riveted joints it would be only D. So D will be the diameter of the rivet itself. Now, as far as primary load calculation is concerned, again the same thing, number of bolts or number of rivets. The next element is secondary. We can directly use this formula. There is no need to derive all this thing. Directly P1 dash, P2 dash and P3 dash can be well calculated from the formula itself. And now, after calculating these from this formula, we'll have to substitute the values of these P2, P3, P4, and we'll have to take the maximum of R max. That is, R max is maximum of R1, R2, R3, and R4. And after calculating all this, we can get the diameter of rivet. Similar is the case with the. I again going back to this, because since it has to be completed. So after this strength of riveted joints and the efficiency, we have to go back to this particular slide. Efficiency, and then type of loading, then eccentrically loaded riveted joint. This is what I have discussed right now, and I hope you are getting the things with reference to both bolted joint and riveted joint. Now, as far as welded joints are concerned, the basic classification will remain same. So here the type of welding and arc, that is fusion and arc welding. So here I think we must finish up. So tomorrow we will continue with the type and numericals on both the elements, and then the remaining part of the lecture. So thank you so much for today's lecture. I hope you have got the things which were shared here. Thank you so much. Madam.